like in this example of holography, how to study Witten diagrams coming from scattering of states at infinity. But there's another way to do the same computations using causal duality. So today I want to explain how to do that. And the reason is just more. You can argue that it's equivalent to doing the story with the back reaction, but it turns out to be easier to compute using the causal dual setup. So what does this mean in general? Suppose we have a field theory on R times X. X can be anything, and R is a topological direction. If I take a point X in X, then the observables of the theory at X, so maybe some little ball around X, will be an associative algebra. So here we're only taking into account, say I set like X, 0. We're only taking into account the product coming from the OP in the time direction. It has other structures coming from the OP in the X direction, but we're just ignoring them for now. So what I want to explain is what the causal dual of this algebra is, and the meaning of the physical meaning of causal duality. So let's suppose that the effective theory on OR is trivial, coming from the compactification OR. So this is going to imply that I can take any observable and take its image in this trivial theory. The observables there are just C. So we get a homomorphism. This is called, in math language, people call this an augmentation. Okay, so from this data, we can build another algebra called the causal dual. A shriek. So it's formally defined by it's defined to be the symmetries of this rank 1 module. So C is a rank 1 module for A. So the formal definition, it's whatever symmetries we have of this rank 1 module. But that's not very helpful. So it's better to think about its universal property. So the universal property is like the Costello dual has a nice universal property whose physical meaning will be very clear. So the universal property is if B is another, say, differential graded algebra, then home maps from A shriek B is equivalent to Mark-Cartan elements A tensor B. So let me explain what this is. So this is the set of alpha in A tensor B such that alpha becomes 0 in just C tensor B. So the kernel of this map is some ideal, and we divide by that ideal. We want to say that alpha becomes 0. This is a degree 1 element, and d alpha is half. And it satisfies that equation. Okay. So Costello dual is this universal property in terms of the Mark-Cartan equation. So why is this relevant for physics? So let's think of B be the algebra of operators of some quantum mechanical system. So then we want to couple this as a line defect on or times x inside or times x. So in general, to couple them, you need to give some. This is the operators of the quantum mechanics. A is the operators of the bulk theory. I need to give some operator, which will be the Lagrangian, which couples them. If I take some alpha A tensor B 1, then by descent, so this is a local operator of ghost number 1. I'm in a theory with topological direction, so I can descend it to a 1 form. Becomes a 1 form, alpha tilde on 4 times x, valued in operators of the coupled system. So we can deform by integral tilde. And it turns out that you can show that this Mark-Cartan equation is the condition that this is a consistent deformation that satisfies the quantum master equation. So here's a heuristic to understand why that's true. If I draw my line, this is x. I have a bunch of things I'm integrating. The failure to satisfy the quantum master equation could be because one of these terms was not BRST closed, so now I would have D. Or there might be something involving two guys colliding, which will give me alpha alpha. So the two possible, so the failure of the quantum master equation is clearly tied up I mean, it's pretty clearly given by the Markov-Hahn equation. Okay, so that's so this is the physics meaning of the conjugal joule. Halms from the conjugal joule are Halms from the conjugal joule are the same thing as ways of coupling in a quantum mechanical system. So there's a small subtlety that we wanted this guy to vanish when I apply this augmentation. So that subtlety is explained as follows. So Halms H weak B, ways of coupling B. B as a line defect. With one more constraint, so it's such that when I integrate out the fields living on X to pass down to something living on OR again, such that when we dimensionally reduce to OR along X, well, if we dimensionally reduced original field theory along X, my assumption was I get the trivial theory. So now I'm going to get something the size of E. But it could be that I could have written a term in the Lagrangian which deformed it. I mean, there was nothing stopping me writing a term which just depended on these fields and did not depend on the bulk fields. But the condition, this condition is the condition that I haven't done that. So we cover B again, and not deformation. Okay. So any questions about this? So we're gonna, it's kind of annoying to have to keep talking about this condition here and the augmentation, so I'll tend to not mention it. But this is, if you're worried about it, this is where it comes in. Okay, so we were interested in chiral theories. So this is, the original definition of conjugal duality doesn't really make sense for chiral theories. However, it's totally possible to make sense of this kind of thing. I have a theory with a chiral direction. I can just, look at the universal quantum mechanical system I can couple. What does that look like? So let's explain how that works. And then we'll see again. So I'll do this for holomorphic Chern-Simons and Kodaira-Spencer theory, and we'll see how the algebra we get looks a bit like the large N algebra we studied earlier. So consider holomorphic Chern-Simons plus Kodaira-Spencer theory on C3. We take C inside of C3. So So we want to define the causal dual of local operators to be the universal chiral algebra living along C, which is coupled to Kaderer-Spencer theory, this holomorphic Chern-Simons, in an anomaly-free way. Okay. So being coupled in an anomaly-free way is the same as having a solution of the Mark-Cartan equation in that picture. And why do we want the universal thing? Obviously, A Schweik is the universal thing with the map from A Schweik. Like A Schweik is the universal thing that I can put there, the initial object of the category. So let's see how to compute what this looks like. And I'm going to mostly focus on the holomorphic Chern-Simons piece for the usual reason that the Kaderer-Spencer piece is just a bit messier. So what does this look like? So if C is the universal chiral algebra, then C, well, let's try, I think, C can be coupled to holomorphic Chern-Simons theory. So we're going to have elements TA or S in C, which couple to the holomorphic Chern-Simons gauge field by L over C so that what am I saying? So what we're saying, like, if we have any chiral algebra, like, what are the possible couplings I can have? I can imagine a coupling to the holomorphic Chern-Simons gauge field and its derivatives in the normal direction. So, like Wi or normal. I could also, if I try to differentiate this along this plane, then by integration by parts, I could move it over here. So I wouldn't get any new operators. I would just get derivatives of operators I already had. So by doing a similar thing, so here, sorry, A is a Lie algebra index. By doing a similar thing for the Kaderer-Spencer field, we conclude that the list, that this algebra A must be generated by things like this. C. It's generated by TA or S and the Kaderer-Spencer field analogs. Okay, any questions? Is making sense to people? Or I know it's a bit of a leap in abstraction from the previous discussions.
Sorry, I'm a little confused here.
Yeah?
Yeah, you were talking about topological versus R.
Yes.
There is this homomorphism.
Yes.
What's the precise word?
So what we're doing is like we don't have a priori a definition of causal duality for holomorphic things. So I want to take this equation as being a definition. So whatever the causal dual is, maps from it are the same as ways of coupling chiral algebras. So now that tells us that this guy must be the universal chiral algebra that I can couple.
But if we take, say, one of the complex plane, replace it with a cylinder and dimension reduce it,
Yes.
does it reduce to that?
Yes, it does, yeah. Although, I mean, it certainly does in practice, though maybe in theory there's a bit of work to do. But if you start with a situation like this and reduce it on a cylinder, you would recover this.
So what is the analog of A here? Is it the analog of two sides?
Over here,
Yeah.
here we were like in an abstract setting, and I wasn't telling you what fields we had.
Right. So what was A here? What is that in this case?
Sorry, overuse of the word A. Over here, A was the algebra of operators.
Right.
And over there, A was the gauge field. So for this example, like here I could have started on like or times CP1. For that example, this could have been X. And here I could have put 4 Chern-Simons. And then you could say, what's the universal thing I can put here? Well, I can couple the Z derivatives of the gauge field. Okay. So the universal thing here will be generated by the generators of the Yangian.
Right. So I guess what I was asking is that so here we have an algebra A, and we're constructing the causal dual of A.
Yes.
So what is the algebra whose causal dual we're constructing here?
The algebra of operators of Guattari-Spencer theory, homomorphic transcendence.
Okay.
So here, yeah.
So so how would you write down the generators of that original algebra in terms of the connection?
The generators of the original algebra would be written in terms of the ghosts. So just like it would be here. Okay, so here I think it's pretty clear that if we think, what is the most general thing we can couple, it will have these operators in it. And let's think about where, like, what are their quantum numbers? So these P, A, or S form a representation of SU2 or, which is of spin or plus SO2. They live in the adjoint of GLK/K. And what else? Oh yeah, and their dimension is or plus S. Over 2 plus 1. There's an extra plus 1 because, well, these things, the normal coordinates have spin half. But there's an extra +1 because I want this to be something I can integrate. And there's no dz here, so I have to have an extra dimension of 1. So this matches exactly what we found in the open string sector of the large N gauge theory. We had these operators I, Z, I1, Z, I, in this case, K, J. So these guys, I mean, they have the same quantum numbers as what we would find in the single trace operators of the large N gauge theory in the open string sector. And if you similarly do the computation of the closed string sector, you would again find a match. It's a computation I'm not going to do here, but it's not that hard.
So is this statement of holography that given a direct Ball theory, its holographic duo is in this sense the universal theory that you can couple to the boundary of the ADS?
Well, it's not the boundary of ADS because there hasn't been any back reaction. There also is no N yet. So the statement is going to be just on C3. I look for the universal theory, universal chiral algebra I can couple along C, which is not anomaly free, but whose anomaly is proportional to N. Some particular tensor proportional to N. And then that universal theory should be the chiral algebra. Well, there's a couple of ways to see it. So in Kaderer-Spencer theory, some of the fields are gauge fields for the SU2-OR rotations because I have diffeomorphisms. Now, if I look at the very lowest lying fields of Kaderer-Spencer theory, I'll find I'm coupling some kind of C ghost for those SU2-OR transformations to my chiral algebra. But there's a central charge. So that will be the anomaly. The central charge is a function of N. So another way to say it is that the anomaly is going to be, if I consider Kaderer-Spencer theory, in the background of some alpha, where d bar alpha is a delta function, this is the field sourced by the brain, then alpha does not satisfy the equations of motion. So studying the theory, so the theory in the presence of this field looks anomalous. So it's that anomaly. So it's related to the field source. Okay, so we'd like to be able to use this idea to compute the OBEs. You want to say, I write down. In my chiral algebra, what equation did these guys have to satisfy to make the whole system anomaly free? And that will tell us what OBEs these guys must have. Okay. So to leading order, in the coupling constant, we must have let me just write down what happens for the lowest lying ones. There's going to be a similar equation for the other ones. It's a bit more complicated. They must have this OB. So how does that happen? Well, so if I look at the integral TA 0, 0, AA, I want to make this to be a gauge invariant quantity. So let's see what happens when I vary A by a gauge transformation. So the gauge variation of that guy is integral TA 0, 0. Let's see actually. D bar ghost field plus a half so this is just the usual gauge variation, this gauge field. So this has to cancel with something. This guy is non-zero a priori. Now consider this must cancel with the gauge variation of the double integral here, this is my plane where the chiral algebra is living. Here I have this operator coupled to the external gauge field. This term must fail to be gauge invariant in a way which cancels that. So how does that happen? Let's look at the gauge variation of this guy. We're only interested now in the terms of the linear guy's gauge variations. Delta of that is the integral of, say, TA d bar C to BA. So on one point I have d bar C, one point I have A. And recall that when I have these two operators in this plane, I'm taking their operator product. So this can only happen if d bar of the operator product picks up a delta. Integrate by parts. TA Z1, TB Z2. So this thing here must be a delta function. Therefore, So the OPE, TZ2, must look like T over Z1 minus Z2. And if you fiddle around with it, the Lie algebra indices also all work out. Was this understandable? I feel like the chiral algebra version of this thing is more difficult to understand than the associative algebra version. Can people follow this computation? I mean, if you want the associative algebra version, it's in a paper with Masahito. We studied this for the Yang. You insert a Wilson line, what's the most general way to couple a Wilson line, what relations must they satisfy? And in the case of a Wilson line, you had, instead of having a 1 over Z, you picked up boundary terms to be satisfied. Here, I suppose we could also, another way to think about this one is we could have, for this diagram, I could introduce a point splitting regulator where this point was not allowed to go too close to that point, and study the anomaly in the presence of that point splitting regulator, which will be the contour integral around a circle. And that must cancel that one, and that forces you to get the 1 over Z minus Z2 pole. Okay, is it making sense? So here we expect that this cardinal dual algebra is equal to the n equals 0 version, where I removed like this n slash n. And then goes to infinity. So what does this mean? Concretely, it means we take the same, to compute the OPs in the chiral algebra, we write down some planar diagrams, which come with a factor of n to some power, and I just drop all the higher. You just kind of drastically restrict the diagrams you can. So in any case, so does this really work? So T00 is supposed to correspond to Ij, and indeed Ij looks like 1 over Z Ij plus n over Z squared. That term goes away. So Ij. So similarly, in principle, you can calculate the T or S OPEs should match these OPEs. And there's going to be a very similar OPE, given by the same computation, one of which is TA or S, TB, AB, with F, A, P, C, PC, or plus L, S plus M. This corresponds to the, here I have a bunch of Z's, Z and I, J, Z, Z, I. These guys have an OBE where I just contract this thing in the middle. And this is a 1 over Z. This is a 1 over Z. So you can really see explicitly the leading OBEs by this causal duality. So maybe just to be clear, so if I had more things contracting there, that would bring in powers of n, would not contribute. And other diagrams where things contracted with tails on the other face would be beyond the planar limit, which we can in principle compute, but is not in this particular computation. Okay, any questions? I feel I've. Here? Oh no, OR is the number of, I mean, there's OR i's which are 1 and S i's which are 2. The index I takes values 1 or 2. Okay, so I suppose now we sort of understand how to do these computations. So let me explain the general rule for doing these causal dual chiral algebra computations, not including the back reaction. Including the back reaction, it gets a little bit more complicated, but not that much more complicated. So we want to consider a diagram in the diagram in the presence of the defect. Something like, I'll draw my defect like that. So this is an example of a diagram where on the vertices here, t0, 0, t0, 0. This is an example of a diagram that will contribute an anomaly. So study maybe using a point splitting regulator if there is an anomaly. That is, you study the gauge variation and whether or not the answer is 0. Here the answer is yes, the anomaly is integral del z1c del z2a e00 squared. This is the ghost. So I've done a gauge variation. I put a ghost there. I didn't put a ghost there. So I get this local quantity, perhaps arising at the boundary after doing a point splitting regulator. And then we know that this anomaly must be cancelled by something else. So in this case, we think, well, what else can cancel it? This is a del z1. This is a del z2. So this must be, the things that can cancel it are something involving t10 and t01. So we read off from the number of derivatives in the fields C and A, and what appears here that there must be an anomaly. Or sorry, that we read off that to cancel the anomaly, what the OPE coefficients have to be. T10, T01 must look like 1 over z T00 squared. And this is an order 1 loop, so there's a h bar and there's a h bar there. Right, so this term comes from asking, say, here, T01, T10. Well, I don't know what the place here. This is coupled to T02, T01. So del Z1 is coupled to T10, this is coupled to T01. I want that the gauge variation of this must cancel that. And that can only happen if the OPE of these guys is 1 over z times T00 squared.
I thought we were talking about chiral algebra. How this H bar here?
So there's a family of chiral algebras depending on the string coupling constant of the bulk. So this particular term goes beyond, like in the holographic single picture, this goes beyond the planar limit.
And then how is H bar and 1 over n compared?
So if we take the usual, let's see. H bar measures what, I mean, in the usual story with planar diagrams and so on, H bar measures what goes on beyond the planar limit. So I suppose, I suppose you could write H bar equals 1 over n. I wasn't really thinking about that because I was thinking in this kind of funny case where n is effectively 0, you can still go beyond the planar limit. Right? So I imagine there's some way there's some various scalings by which you can rescale n and h bar in certain ways. So anyway, so if you kind of stare at this, you can kind of see how in principle you could, like in principle, in practice it's going to be very difficult, but in principle how you would compute any number of these kinds of things, because suppose if I had some derivatives over there, then I would be forced to have 1 over z to the higher powers of z, Because d bar of a higher power of z is a derivative of a delta function. That will give me derivatives. So you can, in principle, read off lots of OBE coefficients in this way. So this particular computation of that diagram, I did this in one of my papers about 5D things. And what it corresponds to is if I take my open string operators, two such open string operators, actually, this case is the simplest one. There's just one z in the middle. These have an OBE where I can track that with that. And I get a product. I get a product of ij. So I get T10, T01 is 1 over z times T00 squared. And it's one order beyond the Taylor limit.
This answers the question that which algebra, which type of algebra we can couple on analysis to.
Yes.
Right?
Mm-hmm.
But so how do I see that this is the same algebra that would appear after the back reaction at the boundary as a dual of the same terms?
Well, remember, this is like a simplification of the truth that we haven't included the back reaction at all, or the parameter n. So there's a generalization of this story with some more complicated Feynman diagrams, which I mean, I don't have time to do any computations, but I can just say a little bit about it. So to include n, all we do is we draw our defect and we have a special kind of dashed line. This is coupled to the identity operator in C, and the field it sources. The source is n times the back reaction. And then we just do the same computation where I have both this dashed line and the usual propagator. Let's do an example. Suppose we wanted to compute that the 2-point function of the JLK/K current looks like 1 over z squared times n. So we can look at how to compute this using these diagrams, and then we can get the right answer and also recognize its interpretation in terms of back reaction. So how would I do this? So this guy is related to the Holomorphic-Simons gauge field. Since these are my inputs and those are my outputs, over here, I don't have any operators. So the thing you want to do is to study the anomaly for this diagram. Okay. So, okay, so we should look at, is this diagram gauge invariant? Well, the gauge variation, so we'll pick up a d bar c. and I can move C, that d bar, over to this line. And you look at this expression, this guy satisfies that. This is the Bochner-Martinelli kernel, d bar of it is a delta function on this line. So the gauge variation is the integral over C of A del C times n. Because this is a factor of n. And then we notice that there's a derivative here. So I think you can convince yourself that this can be cancelled if one over z squared n. The reason we get 1 over z squared n, that comes from this diagram. T00, E00, A. I do a gauge variation, I replace 1 by d bar, and I'm going to apply d bar to the 2-point function, and you want to get that expression, so you want to have a derivative of the delta function appearing, so this will be 1 over z squared. So you can. So this doesn't yet answer your question, but this shows that you can actually compute things which are functions of n, like the n-dependence of the 2-point function. But the answer to your question is, suppose I wanted to study such just a general 2-point function. Then I would have an arbitrary number of dashed lines. But the dashed line just is the back reaction. So therefore, this process is the scattering of a particle from infinity in the back reactor geometry.
So in general, do you expect the algebra that you get by including this back reaction in different from the algebra that you get without the curve?
Yes. So so in this example, before I introduce this back reaction, this factor of n, and these dashed lines, this operator didn't have any 2-point function.
So in the case of the young level that is special because
yes, because some of the back reaction didn't really. This wasn't a space-filling brane. You could move it away from the actual brane you cared about. So, okay, you might ask, what's the point of this, given you could try to compute in the back reaction? And the answer is, beyond tree level, Witten diagrams are very hard to compute. But I mean, these diagrams are very easy to compute, at least at the 1 or possibly 2 loops. Says any other questions? Maybe I'll stop there. If it wasn't too unclear.